Okay, so Rolle's theorem and mean value theorem is what we're going to look at. And basically, these are what probably the first time we've ever done this in math, which is, these are called an existence theorem. Sometimes there's something that you really think exists or you're looking for a solution. Great pain is taken in the real world to actually make sure that what we're doing has an answer. So sometimes people have even gotten like their PhDs just by proving they didn't actually find the solution, they just proved that one exists. And there's a lot of famous work out there that they didn't actually solve the problem, they just proved that an answer exists. So luckily for us, Rolle's and mean value theorem are pretty simple existence theorems. And I'll show you a picture of Rolle's to get us thinking about what it means. So here is a, since my artistic skills are so good, I've got a picture of one here. So this is what Rolle's theorem is, and basically what I'm trying to show you here, here's the algebra, right? The stuff that you probably don't want to hear first. First we'll look at this picture. So if we look at this picture, basically what it says is, if you have an interval from A to B, and f of A is the same value as f of B, there must be a point where the derivative equals 0 in the middle somewhere. Now, because we're talking about derivatives, we have to be very careful. Someone could be very clever and they could fool us. I'll show you an example in a second. It has to be differentiable everywhere in there. It has to be a nice smooth curve. Otherwise, the point where we expect it to be equal to 0, it may be undefined. There may be problems there. Okay? So what we're going to do is, before we write down the technical definition, we're going to try doing our own Rolle's theorem here. So for example, apparently I need to recalibrate. So I'm just going to do any old graph. You're welcome to do any graph you like as well. Maybe I'll go like this. Let's use red. I don't know why I'm so partial to red, but let's just say it went like, I don't know, something like that. Okay? So the conditions again were that you pick any interval you like. So why don't we pick the interval from, I don't know, let's say, I'll pick this interval here. So the first condition is that the values have to be the same. So they have the same value. F of A is the same as F of B. And here's my function at A. Here's my function at B. Here's A. And here's B. Okay. Now what it guarantees, we can guarantee the existence of a point where the derivative equals 0. So you didn't have to draw the same graph as mine, but as long as it's differentiable, somewhere in the middle there, this must exist. Okay? So this is the picture when you want to think of for Rolle's theorem. And I'm going to show you now the, I'll put back up the technical details that you need to have written down. So specifically what we're saying is, if f is, let me see here, I can probably zoom in on this. If f is continuous on the closed interval AB and differentiable everywhere inside, then, and f of A equals f of B, there must be a point where the derivative equals 0. So I'll let you copy that in. Okay, so let me just show you here why it has to be differentiable. For example, sorry, I'll put it up again in 1 second, Anthony. So for example, so here's a well-known graph to you, one at which, I don't know, let's say I go to -2 and I go to +2. That means this value is equal to this value. Is there anywhere in there the derivative equals to 0? No, it was able to cheat and get around it because it's not differentiable. So that's just one example of why things can go wrong if we don't have a nice smooth curve. Okay, so again, with an existence theorem, all we're going to do is we can use it to show that something's true. So for example here, if I'm going to use Rolle's theorem, let's determine an interval in which that has at least one critical point. So I'm going to put it up on the screen so you can see that graph. So it's x to the 4 minus 2x squared. And I'm going to make my range, let's try, I don't know, negative 4 to 4, 10 and 10. Something about like that should give us a good picture. Okay. Actually, I can probably even make it a little better if I go like this. Okay, so here's the graph. And if we're just going to state it with Rolle's theorem, if I'm looking at the picture of this, here's one point up here. That's a nice natural choice because it's a nice easy point at negative 2, 8. And over here at positive 2 and 8, I have the same value. So I'm going to choose that for my interval. So let's choose the interval from negative 2 to 2. And now we have to ask ourselves, is it differentiable everywhere inside there? Yeah, hands up if you think so. Yes, it's polynomial. There'll be no problems. Okay, so that means somewhere in there, f of negative 2 equals 8, and f of 2 equals 8. So we can say, therefore, by Rolle's theorem, there is at least one place where that function has a derivative of 0. So again, that's one nice thing about people who work with existence is they don't actually need to find the answer. It's enough to just state that it must exist because of Rolle's theorem here. Okay. And again, if you look at the picture you can see, I can see 3 places where it's equal to 0 in that picture.
Three places.
Yep, so 3 places.
Where x equals negative 1, where x equals 1, and where x equals 0.
Yep, that's the ones. But the point is there has to be at least one. There was 3 in that case, but there has to be at least one. Okay, so Rolle's theorem. Rolle's theorem is basically a lead up to the mean value theorem. Rolle's theorem is one specific case. Rolle's theorem is used to prove the next thing, which is the mean value theorem. And it has a bit more general, same idea, but it's a bit more general in those terms. So what I'm going to show you here is, again, we'll start with a picture of the mean value theorem. And then we can talk about what that picture means. So this time what it says is you can take any 2 points, for example, f of A and f of B. If I connect those and I make a secant line, somewhere in between there must be a place where the derivative has the same slope. So basically I'm saying the tangent line equals the secant line for some place in the middle. Okay? So if we were to write that out as a formula, it would look like this if I'm trying to say the derivative equals to the secant line. This is your slope formula from before calculus. This is your calculus slope. So it's basically, if you think about it, all we've done is we've taken Rolle's theorem and we've tilted it, right? If we were to tilt this, maybe turn your head in a funny way, it'll kind of get flat again and do what Rolle's theorem does. But this says it doesn't have to be that the graph equals 0. Oh, sorry, that the derivative equals 0. It works for any slope. Okay, same conditions. It's continuous on AB, differentiable inside, and there must be a point with this property. So we'll find that. We'll verify it again with mean value theorem. Well, I'll give you a minute just to write it down. Okay, so again, I invite you to draw any graph that you like, but I don't know. Let's try this time here. Maybe I'll go something like that. And take any 2 points you wish. You don't have to follow me in this one, but maybe I'll pick these points, I don't know, let's say here and here. So here's my secant line, and I would bet that probably about here, there's a tangent line that's parallel. Okay? Or sort of parallel, I guess, depending on your artistic skills. So again, if I was to write this out, this is the derivative, and this is a slope like before calculus. So if I want to make the equation up, I say there's a point where the derivative is, here's f of b, it's at the point b, here's f of a, which is at the point a. So the slope formula would go f of b minus f of a all over b minus a. So that's the mean value theorem, and that's where it comes from. So having the picture in your head is good. It helps you remember what the theorem says. Okay, and we're going to try this in the next equation below. Anybody object to moving that? Did anybody draw their own graph? I'm always curious. So no, two creative people, 3, 4 creative people?
It's not all that creative, it's rather basic.
Okay.
And it's x squared minus 7.
Okay. So again, in this example, we're going to take a look at the interval from 1 to 4. So here is from 1 to 4, okay. And the points that I'm interested in are f of 1 and f of 4. So this is a nice smooth curve. It would be differentiable everywhere that we're interested in it, from 1 to 4. And we need to find its derivative because we want to find where is this point where the secant line, here's my secant line, equals my tangent line. So let's find the derivative. I guess I would probably write this as x to the negative 1. So using my power rule, negative 1 comes to the front, it'll become positive 4, x to the negative 2, or 4 over x squared. So I'll use that derivative then. I would like to know, where does this derivative equal the plain old, math 10, math 11 type of slope? Okay, so I need to know what is this slope. If I don't know what the slope is, I won't be able to find the tangent. Okay, so in my picture, that's at 1, that's at 4, and this is at 1 and 4. So the slope is going to be 4 minus 1 over 4 minus 1. So the slope is 1. I'm looking for a place then where the derivative equals to 1. So where does 4 over x squared equal to 1? So where does 4 equal x squared? There's a couple of places. We're only interested in one of them though, because negative 2 is out of bounds. We're not looking for the negative 2. That's not in our interval. So we would knock it out.
I think I found it.
And up here at 2, if I try and do my best tangent line, we can verify that those two in fact are the same value. The secant line equals the tangent line there at x equals to 2. Okay, so I'm not sure that this is the greatest example, but sorry, people still looking at that, I assume. Is that all right if I leave it there? It's not the greatest example, but I guess whenever you get a speeding ticket, there's always this argument, right? So let's just say a trucker goes through a toll booth. So you know that in two hours from the time she got the ticket in the toll booth till she stopped, she's gone 159 miles in 2 hours. Okay? So assuming she didn't just rip through the toll booth and grab it on her way, right? She probably stopped to pick up the ticket and then go through the toll booth, right? Pay her toll. So assuming then that when she started, she was going 0 kilometers per hour.
It says miles.
Or, oh, sorry, yeah, we're using miles here, so thank you.
Some obscure reason.
Say she started at 0 miles per hour because that's when she picked up her ticket. Then 2 hours later, at time equal to 2, she has gone 159 miles. So we could calculate her average speed over those 2 hours. So something that you physics people have probably done many a times. So she's position 0 when she starts. So I guess we should really say position 0. And she goes 159 miles. She does that in 2 hours. So her average speed is 79 miles per hour.
79.5.
79.5, right. So unless she has figured out a way to break through space and time, and you know, she doesn't have a smooth, continuous speed, right?
And doesn't wind up landing on some other vehicle.
Okay, fair enough. This is a smooth. This is a smooth curve. So because we have a smooth differentiable curve for speed, that means somewhere in the middle, I don't know when, I mean her speed might have gone like this, it might have gone slow, and then she might have just ripped it for the last, you know, little bit, and then, you know, back down to normal. But somewhere in the middle there, I don't know where, if this is 79.5 miles an hour, I know she had to have been going at least 79.5 miles an hour somewhere else. She might have been going faster, she might have been going slower, but at some point you were speeding. So anyways, that's the best we're going to do for our level of existence proofs today. Okay, so for homework tonight, the exercises are listed below.